Hello, welcome to our presentation on simple algorithm for correction of MRI image artifacts due to random phase fluctuations. This paper presentation is done as a part of medical imaging course at IIT Tirupati. I, Bhargav Reddy and Harshvardhan Reddy as a team present this paper. I deal with the introduction and the need to go for this algorithm for phase correction to remove artifacts. And Harsha will describe the algorithm and conclude. Introduction. In this paper, the author proposes an algorithm to enhance the MRI image with artifacts caused by random phase variations due to field instability. This is an algorithm that can correct the random phase variations induced by field instabilities without prior knowledge about the phase error. At first, let us know what are artifacts in medical imaging. In medical imaging, artifacts are misrepresentations of tissue structures produced by imaging techniques such as ultrasound, X-ray, CT scan, and MRI, which distort the true information about the tissues. Generally, artifacts are misrepresentations of tissues which change the true information of the tissues. Fast field cycling, in short FFC. Fast field cycling is a technique that involves varying the main magnetic field B0 during the pulse sequence. The term fast indicates that the duration of transition between the two fields is much shorter than typical T1 value of sample investigated. Use of FFC. Using FFC, one can measure the field dependence of relaxation rate of a sample and infer information about its structure. So this is a very useful technique to study about structure of tissues. This diagram represents variation of T1 relaxation time of different tissues with respect to B0. B0 is main magnetic field and T1 is relaxation time, which is a measure of relaxation rate. Observe the variation of T1 for different B0 values for different tissues. Notice that this variation of T1 with B0 is also different for different tissues. This helps a lot to study the structure of tissues under study. Drawbacks in MRI. Cartesian MRI acquisitions rely on the magnetic field stability in order to maintain the phase information across k-space. Maintaining magnetic field stability may not be possible due to noisy environments. For example, if MRI mission is near to elevators or roads, or when motion occurs, like movement occurs by the person under scan, like when the person moves during the scan. In these during these situations, it is very hard to maintain the magnetic field stability. So generally, magnetic field stability is hard to maintain in MRI. So our challenge in this method is to stabilize the magnetic field during the acquisition of NMR signal for using FFC in MRI, which is hard to do. A typical consequence of field instability is small random phase variations between each line of phase space resulting in artifacts. This is similar to those which occur due to homogeneous motion but harder to correct as no assumption can be made about the phase error, which is completely random. Need to go for algorithm. One could measure the field fluctuations and deduce the phase corrections to apply to the image, but that requires a fast field probe with sensitivity of the order of parts per million at nominal field of 200 millitesla, which we do not currently have. Therefore, a post-processing correction technique, that is an algorithm, is required. The algorithm presented here is a simple post-processing technique both in k-space, that is in frequency, and image space, that is spatial domain. Introduction to the algorithm. The algorithm exploits the fact that the ghosts caused by the field instability manifest in the image regions which should be signal free. This is the first hand description about the algorithm. The algorithm minimizes the signal in the background by finding an optimum phase correction for each line of k-space. It repeats the operation until the result converges, leaving the background free of signal. It takes advantage of the fact that random phase errors between k-space lines lead to smear across the entire image so that signal-free regions only show ghosting. Our friend and our classmate Mr. Harsha will take on from now with in-detail description of algorithm. Thank you.
Hi everyone, I am Harshavardhan. I am going to discuss algorithm for the correction of MRI image artifacts due to random phase fluctuations. The algorithm developed here mainly focuses on acquisitions made using Cartesian k-space sampling. If we see the structure of the flowchart, we can mainly see two loops, two iterative loops. The first red color loop is used for estimating the background of the image. The second green color loop is a SQP optimization loop, which we use for estimating the phase errors. The input to the algorithm is a complex image that we obtain after performing 2D fast Fourier transform on it. Initially, we reconstruct the image by using inverse fast Fourier transform, and then we segment the reconstructed image into background and object by applying thresholding on the magnitude of the image. At this moment, the background is coarsely estimated because of smear in phase encoded direction. Here, at this moment, we can also give our guesses for background estimation. After this, the algorithm then estimates the phase correction for all phase encoded k-space lines using sequential quadratic programming method. In sequential quadratic programming method, at each iteration, phase errors are estimated. The image is reconstructed with the estimated phase correction, and the amount of signal in the background is extracted for use as a minimization criterion. This loop continues to run and we get a partially corrected image. After getting a partially corrected image, we again perform the segmentation and extract the background from the partially corrected image. For this background, we again apply SQP optimization loop to get the phase corrected image. And if the variation between the new phase error estimation and its previous value is greater than a threshold, then algorithm re-estimates the background using the best corrected image and reiterates the phase estimation loop. And these two loops run continuously, and if the phase is converged, we get a corrected image. Here in this figure, the A image is a reference image. It is a 128 by 120 image selected from stack of images acquired on a stable FFC-MRI scanner. Here the region inside this dashed rectangular indicates the signal-free region. Here the B image is the degraded image obtained by the addition of random phase along each phase encoded line of its k-space. We can clearly see the ghost image here in the B figure. Because the phase is here, the ghosting happening in the horizontal direction. The graph here gives the comparison between the phase error in the original image and the estimated phase error. In the graph, the blue line here indicates the phase error in the original image, and the dashed orange line here indicates the estimated phase error with the help of our algorithm. Now we see some examples where we applied our algorithm. Here the A image is a raw image acquired from a 0.2 Tesla FFC-MRI scanner. Here in this image we can also see the ghosting in the horizontal direction. After applying our algorithm, the result is shown in the B image. Here we can see the ghosting is removed and we get a better quality image here without any noise. Here the C image is a raw image of a cylindrical phantom acquired from a 0.5 Tesla FFC-MRI scanner. And after we apply our algorithm to this image, we get this image as shown in the D figure. Here we can also see the ghosting in the horizontal direction is removed and we get a better quality image. This corrected version of the D image is obtained in 21 seconds and this corrected version of the B image is obtained in 2.9 seconds. Conclusion. Here we are able to get a good estimate of the random phase error. By this we can know the origin of the error and we will also able to better estimate the image and with we can get an image with sharper details and better quality. Here we are using SQP method, sequential quadratic programming method, for estimating the phase errors. We can also use other methods because SQP may not be an ideal one. We can use method like simulated annealing and we can check the results. Here we also restricted our algorithm for Cartesian acquisitions only. We can also use for other trajectories but with modifications. Here the algorithm we developed can also be used to correct random phase errors in one direction of the case space elsewhere also.